All right, so we are starting into chapter 2 today. Chapter 2 concerns atoms, ions, and molecules. And we're going to be kind of going off of that to eventually kind of get into a bigger picture idea of what the atom is made out of and how to do some really simple basic calculations around atoms. So we're going to start with this nuclear model of the atom, which is our current model of the atom, or at least the simplified version of our current model of the atom. And what that model of the atom does is it tells us that there's this tiny positively charged nucleus in the center, and that nucleus has all of the mass of the atom inside of it. Inside of that nucleus, we have a proton, which is positively charged. Proton, we will designate as P plus, and the neutron, which is electronically neutral, and 0. So inside that nucleus, we have protons and we have neutrons. And the proton's purpose is to provide positive charge. The neutron's purpose is basically there to keep all the protons apart so that the nucleus stays together. Now, there is a third subatomic particle. This is the subject of Thomson and Millikan's experiments, the electron, E minus. And that electron is surrounding that nucleus and is of a considerably smaller mass. So if you look at the proton and the neutron, what you will see is that the proton and the neutron masses are essentially identical. Yes, they're slightly different. The neutron is slightly larger, but not by a whole lot. And so for that reason, rather than talk about their masses in these terms of atomic mass units, that's what U stands for, we're going to talk about them in relative terms. Since the neutron and the proton are practically the same, only different in the fourth significant digit, we're going to say that their mass number is equal. So we give them a mass number of 1. Since the electron mass is nearly 2,000 times smaller than the mass of the proton or the electron, we're going to call its mass number 0. So that's where these relative numbers come from. So that's a relative term for mass here. That'll come in important when we start to look at mass number to describe different types of atoms. From a charge standpoint, we can see that the charge on the neutron is obviously 0, and the charges on protons and electrons are equal, yet opposite. But instead of monitoring charge in terms of these really small numbers, I mean, we're talking 10 to the negative 19th here in terms of charge. Instead of doing that, again, we're going to go with a relative value of charge. So the neutron's relative value is still 0. But the proton, because of its positive charge, we're going to say it's positive 1. The electron with its negative charge, we're going to say is negative 1. Now, again, these masses here come in terms of atomic mass units. Atomic mass units are a defined value based upon the mass of carbon-12. Carbon-12, which has 6 protons and 6 neutrons, has been systematically defined as having a mass of exactly 12 AMUs. The relative masses of the proton and the neutron on that scale are going to make up a really significant portion of what we will end up using to describe elements in terms of their mass. So atomic mass units are the basic unit for how we describe how big or small an atom is based upon its mass. Now, one of the things that we know about atoms is that even though from a certain perspective, all atoms of an element are the same, we also recognize, based upon experimental evidence, that there are some differing characteristics between types of atoms in the same element. And the first experiment that kind of showed this was this bent tubes experiment. And what happened in that experiment was basically they shot a beam of charged ions into this magnetic field, and it caused the beam of ions to actually split. The lighter beam, because it had less mass, was able to bend more significantly than the heavier beam. And so as a result, they were able to determine, hey, you know, neon actually has two different forms. There's neon that has a smaller mass, neon 20, and there's the neon that has a slightly larger mass, neon 22. But we know that they're all neon. So when it comes to that idea of all elements of the same type have the same looking atoms, that's true to a certain degree. What they do have in common is they do have a common number of protons. So if I count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 protons in this sample of neon 20. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons in this sample of neon 22. So what makes an element has to do with the number of protons, which introduces this idea that, okay, if the proton number is fixed, then the neutron number must be allowed to change in order to get these different masses. And when that occurs, we call that phenomenon, we call those differing versions of the same element isotopes. Isotopes have a common atomic number, that is a common number of protons, but a differing number of neutrons. And so where this will ultimately lead us, because of this idea, is looking at a difference between atomic number versus mass number. Atomic number focuses only on protons. Mass number focuses on neutrons and protons together. So atomic number directly links us to an element. Mass number gives us an idea of what kind of isotope we are looking at for that particular element. And we can put all of that information together in a very condensed form called isotopic notation or nuclide notation. This format has 3 parts. There is X, which is just the atomic symbol for that particular element. We have Z here on the bottom. This is the atomic number. So again, Z is the number of protons. And then we have A, the mass number, which is the number of neutrons plus the number of protons. When we identify an element or when we identify an isotope, we will usually do so by identifying the name of the element or the symbol of the element and its mass number. So here are the 2 isotopes of neon that we were exploring in their now familiar nuclide notation. And so notice, among them, we've got some similarities. Their atomic numbers are the same. Because their atomic numbers are the same, their symbols are the same. The thing about them that is different, that sets them apart from each other, is that number, that mass number, which manifests itself in terms of a different number of neutrons. So when we have two elements of the same kind, but they have different mass numbers, that's what an isotope ultimately is. And we can tell an isotope apart based upon its mass number. And so, in terms of identification, we would call this isotope neon 22. And we would call this isotope neon 20. Again, since atomic number and symbol tell the same thing, we can get that information very condensed in this kind of format. All right, so let's take a little time and do some practice with nuclide notation here. So we've got a few nuclides here that we want to explore. And what we want to do is we want to write out their symbols in the proper notation. So let's start with this first one. We have something that has 2 protons and 1 neutron. So the 2 protons, that would be its atomic number. So 2 is going to go on the bottom. Element number 2 on the periodic table is helium. 2 plus 1 will give me 3, and that's going to be the mass number. So my nuclide notation for helium here is this. We would refer to this isotope as helium-3. For letter B, here I have 54 protons and 75 neutrons. 54 protons, we know that is the atomic number, so that's Z. 54 plus 75 would give me 129 as my mass number. So I've got 129 as the top number, 54 as the bottom number. Element number 54 on the periodic table, Xe, is xenon. So here's my correct nuclide notation. We would identify this isotope as xenon 129. All right, any questions about how to convert information about an atom into nuclide notation or its identifier? If you have questions, either drop them in the chat or just come on the microphone and ask directly. All right, I'll take that silence to mean that we're okay. So let's do another one here. Now we're doing something a little bit different. Now we are integrating the idea of electrons into the mix. And so we have to take into consideration the idea of charge. Now, if there is no charge, then that means that the protons and the electron numbers are equal to each other. Otherwise, we can figure out the charge of any ion by taking the number of protons and subtracting from it the number of electrons. So let's look at example A here. Example A tells us we have cesium. Cesium is element number 55 on the periodic table. So since it is element number 55, we know it has 55 protons. To figure out the number of neutrons, I would take the mass number and subtract from it the atomic number. So 134 minus 55, 134 minus 55 gives me 79. So I have 79 neutrons. Now for electrons, since I have a charge, my charge here is positive 1. I'm going to need to do a little bit of algebra here to figure this out. And if I rearrange, so add electrons to each side, I would get 54 as my electron number. Right. Questions on letter A here? All right, let's move on to letter B. In letter B, I have iodine. Iodine is element number 53. So I have 53 protons. Find the number of neutrons. I would take the mass number 131 minus 53. 131 minus 53 gives me 78. So there are 78 neutrons in this particular isotope of iodine. To find the charge, here I've got a -1 charge. So -1 is equal to 53 minus the number of electrons. Going to have to go through a similar process. -1 plus electrons is equal to 53. Electrons is equal to 53 plus 1, which would be 54. So here in this particular exercise, we've just added that one extra little piece to it. That extra little piece being, what if we have some sort of charge on the element in addition to the atomic number and the mass number? Any questions with how to handle those? All right, again, hearing none. I want you to try this one out on your own here. So on your screen, you should have 3 boxes that you need to fill out. The top one being the mass number, the bottom one being the atomic number, and the one in the middle being the symbol itself. So put in your answers there. And I'll give you a couple minutes to do it. Let's go ahead and talk about this. So again, our proton number should dictate to us two things. It's going to dictate to us the atomic number, 36, and if we have our periodic tables handy, it'll dictate to us the name of that, which is Kr krypton. So just from the protons, you should have been able to get those two answers. Now to get the mass number, I need to add together the protons and the neutrons. So that would be 36 and 47 for a total of 83. So that is the notation that you should have entered into Top Hat. Okay, so we're going to end our discussion today by starting to feature certain aspects of the periodic table. Now, for those of you that are in lab, you got a taste of this doing that elements periodic table activity on Tuesday. But just some background. We know that elements, based upon, if we go back to the earliest days of science and chemistry, we know that for the longest time, people have been trying to group together elements based upon common characteristics, common properties. But it wasn't really until Mendeleev came along that he was able to do something a little bit more systematic. So instead of just saying, okay, these three elements are kind of similar, so they're going to go together, and these ones are kind of similar, so they're going to go together. There's really no rhyme or reason to either of them being where they are. Mendeleev said, hey, we know atomic masses. I'm going to put them in order of atomic mass. And when I put them in order of atomic mass, what he started to notice is that based upon how he arranged it, they started to line up. Okay, I'm going to make 7 columns, and every 7th element has similar properties. Every 8th element has certain properties. Every 3rd element has certain properties. And so he was able to kind of draw out this plan, this guide. And what he was also able to do, and it was really important, was he recognized holes. So for example, between calcium and titanium here, he recognized, okay, calcium makes sense with magnesium, with zinc, they have similar kinds of properties. They all form +2 ions. They all react with oxygen in a similar ratio. Titanium doesn't do that. Titanium is more like carbon and silicon. It reacts with oxygen in a 2-to-1 ratio, 2 oxygens for every titanium. Whereas aluminum is in a 2-to-3 fashion. So he was able to recognize, based on some common reactivity, some common products, hey, this doesn't make sense. Maybe there's an element we just don't know about yet. And so he put these holes in the table saying, look, something has to go here. It would make sense if it did. And sure enough, the reason why his table gained such prominence is because not only was he able to do such a thing, but he was also able to accurately predict some of the properties of the elements that belonged in those holes. Now, in the days since Mendeleev, we've come a little bit further along. In the days of Mendeleev, there was no idea about protons or electrons. We just had masses. But what we're able to do with more information is recognize, okay, it actually isn't mass that we need to arrange ourselves by, but rather atomic number. Because there are a couple of places, and if you look closely on the periodic table, you'll see that there are a couple of places where things don't quite match up the way that they should. But when we arrange it by atomic number, what we'll find is that everything works out very, very well in terms of columns. Elements that are in the same column have similar chemical and physical properties. And that's important to know because that tells us, okay, they belong together, they have certain common traits. And so what the subject of our discussion on Monday is going to focus on is looking at some of those properties and some of those key ideas a little bit more closely. And so make sure that you have a periodic table with you and that you bring that table with you on Monday, because we're gonna make some drawings, we're gonna color in some things. I'm gonna give you some notation that is going to help to kind of make sense of everything. And we'll be able to do things like this, where we categorize and break things down into groups, into families, and predict common charges of ions based upon their position on the periodic table. And so that will be the subject of Monday's lecture.